All right, we're back. This is 4.3. We're chapter 4, page 8 of the note packet. And, actually page 7, sorry, page 7. Page 7, 4.3, multiplication rule and conditional probability. All right, so we're looking at and problems. Or means add, we looked at that in 4.2. And means multiply. And so when we're multiplying, we need them to be independent of one another. In most cases, they can be dependent events also, but we'll take a look at that. That's a special case. So let's see, study for a test, pass a test, independent or dependent. Hopefully that's dependent. I think maybe in some cases it's independent, but most cases, the more you study for a test, the better you do on it. So you're likely going to pass the test. So we'll look at that as dependent event. Own a red car, have red hair. That's likely independent. Again, it could be that you have red hair and decided you wanted a car also that's red because of that. But that's most likely not the case. Most people don't buy cars based on their hair color. That's not always clear cut though. So sometimes we can't really determine for certain if it's dependent or independent. Other times we can. Raining today and then playing golf today. That's likely dependent for most people. I can do my best. Bill Murray, I don't think the heavy stuff's going to come down for some time. Caddyshack. If you haven't seen that and you like golfing, you have to watch Caddyshack. So that's a dependent event. If it's really pouring rain, most people don't go golfing. Raining today, owning a red car. That is definitely independent. I cannot think of a scenario that because it's raining today and then you bought a red car, therefore it rained today, or it rained today because you own a red car. Those are unrelated. All right. And then on the next page, that's the page 8, was flipping a coin and rolling a die. Those are completely independent of one another. And that means whether I get heads or tails on the coin, that has nothing to do with whether I get a 1, 2, 3, 4, 5, or 6 when I roll the die. Those are completely independent of one another. All right? Okay, so let's see. Find the probability. A card is drawn from a deck and then replaced. A second card is then drawn. What is the probability of getting a queen and then getting a club? So these are actually independent events because it's with replacement. With replacement means I put the card back in and then I shuffle the deck up really well. And so one outcome really doesn't have anything to do with another outcome. That's even flipping a coin multiple times. Lots of people don't understand that. They can't wrap their head around that those are independent events. I could flip a coin, a fair coin, 10 times. And I could flip it and tails, and flip it and get tails, and flip it and get tails, and flip it and get tails. So 4 times where I got tails in a row. And then people think, they say, oh, well, now it's got to be heads. Because you were supposed to really get, every time you get tails, you're kind of supposed to get heads. That is true for the law of large numbers. If I flip it 1,000 times and it's a fair coin, it's very likely going to be really close to 500 each. That doesn't mean I can't get a string of 20 in a row of tails and it's still a fair coin. And so you've got to be careful. Those are independent of one another. They're not dependent events. So same thing with this scenario. You pick a card, you look at it, you put it back in the deck, you shuffle it up, you pick another card. So whatever you got the first time, really, it's got nothing to do with what you're going to get the second time. So queen and then a club. So what are the chances? That's going to be the probability of getting the queen and then times the probability of getting a club. But these are independent of one another because you put the card back in. And so the chances of getting a queen, there are 4 of them out of a deck of 52 cards. And there are 13 clubs out of a deck of 52 cards. And so on the next test, if there's anything, I'm trying to think if there's cards on there. If there are cards on there, I'll put a I'll send you a picture that you can use for the test that has like the whole deck of cards laid out face up so you can see what's what. All right. So then if we multiply straight across, top times top, 52, bottom times bottom, 2704, and then that actually reduces. And divide by 52, top and bottom, and get 1/52. So that's not a very likely event. 1 out of 52 times, if you picked a card, put it back in, shuffled it up, picked another card, that you would get a queen the first time and then a club the second time. It's much more likely of that not occurring, which would be 51 52s. All right. Let's see here. 9% of men have a type of color blindness that prevents them from distinguishing between red and green. If 3 men are selected at random, find the probability all of them have this type of blindness. Assume independence. Okay, so since the selection is random and it's a smaller number, we can conclude independence, but they also said assume independence. So let's take a look. That would be the probability that you're colorblind and the second guy is colorblind and the third guy is colorblind. And so this would just be probability of colorblind, CB, times probability of colorblind times probability of colorblind. And so that's just going to be 9% times 9% times 9%. That is not, I'm going to make these into little x's, time signs. Normally in algebra we don't do that, but here it's just easier to see it separated. And so look, 0.729. So look, if I make this into a percent, that's a decimal. If I make it into a percent, it's 0.07 of a percent. 0.07 of a percent. It's not a very likely outcome that 3 randomly chosen people would all be colorblind, even though there's 9% of the people that are. All right. Of course, if an event is not independent, they are dependent. And so we want to adjust for calculating. So the 5% rule, you may assume independence if you sample less than 5% of the population. Okay, so that's just a little sidebar. General multiplication rule, if A and B are any events and A and B, the probability of A and B, and they're dependent, is the probability of A times the probability of B given A, where that looks like this. When they say the probability of B, and there's this straight line and then an A, that's given that. So the probability of this occurring given that already occurred. So probability of A times the probability of B, but given that A did already occur. So this is, we kind of put on, we play pretend. So let's see. Suppose 2 cards are drawn from a deck without replacement. So I'm going to draw one, look at it, draw another one, and look at it. So not put it back in and mix them up. Find the probability they're both aces. So we want to know the probability of ace and ace on a dependent scenario. So this is the probability that you get an ace times the probability that you get an ace given you already got an ace. All right, so let's see. The probability that you get an ace is 4 aces and a deck of 52 cards. Now you pretend like that happened, like you got an ace. So we pretend we pulled an ace. We have a pretend deck here. I shuffled it up really good. I drew a card. It was an ace. Now, how many aces are left? Well, if were 4 to begin with, and I just drew one, there's only 3 left. And now this is very important. This is probably the #1 mistake that students make on these kind of problems. You got to remember to reduce the sample space. There's 1 card out of the deck. 1 ace is gone, so it's no longer out of 52. It's now out of 51. All right? And so if I would have wanted 3 aces in a row, I would have went 4 52nds times 3 51sts times 2 50ths. All right. Okay, so let's figure this out. This, again, not a very likely occurrence. You multiply straight across. You could reduce this. 51 is actually divisible by 3. Oh, that's a little trick. I should tell you that. Look, if you add up the digits of any number and you get a number that's divisible by 3, the original number is divisible by 3. True story. So look, 5 plus 1 is 6. 6 is divisible by 3. Therefore, 51 is divisible by 3. So that's actually 3 times 17. All right, but we'll just multiply straight across and then reduce. So, or we could just reduce first. Look, this is 1, 13th times 1 17th is 1 times 1 is 1, and 13 times 17, oops, you're not going to be able to see that. 13 times 17 is 221. So that means the probability of 1 over 221, let's make sure you can see that. You can. The probability of 1 over 221 means if I were to do this 221 times, if I were to draw 2 cards, 221 times, it's likely only one time would I get an ace, and then I would get another ace. All right? Now, that doesn't mean it can't happen the third time you do it. It's just if you keep doing it over and over again, it's not going to occur very often. 1 out of 221. All right, let's look at the next one. Resident worked with Dave's Cool Insurance for both homeowner and auto insurance. Oh, okay, wait. There's some build-up before that. Dave's Cool Insurance found that 53% of imaginary town residents had homeowners insurance with the company, and these 15% had auto insurance with the company. Find the probability a randomly selected person have both homeowners and auto insurance. Okay, so that would be, let's get rid of this and take a look. So that is the probability of home and auto. And so that's the probability of home times the probability of auto given you have your homeowners with them. And so they did give us those two amounts. This was 0.53. That was just the general probability that you have homeowners insurance with them. But then they said 15% of people with homeowners insurance also had auto insurance. So we get to multiply. Oh, here, I'll make that into an old-fashioned time sign so you can see it. And then, so what is that? Still not very likely. Just about an 8% chance, right? 0.0795. So if we rounded that to hundredths place, 0.08, and then made it into a percent, multiplied by 100, we're talking 8% chance. If we tried to flip it, you can't. They didn't give us info about that. If you said, what's the probability of auto, and then you have homeowners, given, so how many people are insured for auto, and then how many people have home given that they have auto, they didn't give us that information. So we cannot figure that out. So you can't just flip-flop those around. All right. Okay. So let's look at, this is a pet peeve of mine. I do not like that this book and most books that I've encountered don't really do this well with dependent events. They define it like so, and your book does this too. It says the probability of B given A is equal to the probability of A and B over just the probability of A. I don't like that because we just on the section in front here said and means multiply, and so a lot of people just think, oh, I take the probability of A times the probability of B. No. That's not what's going on there. I'd like you to add this in your notes. Put the word both A and B. Just both. Just squeeze the word both in above that. that's both of them occurring simultaneously. So that's like if I said, well, getting a queen and getting clubs, getting the queen of clubs, they both happened at the same time. So that's what's going on with that. All right, so look, let's take a look. The probability, oh no, you get audited and given that you got a speeding ticket. Oh, I hope those are unrelated. Example, some people are less lucky than others. Suppose that the probability of receiving a speeding ticket in a given year is 12%. And the probability of receiving a speeding ticket and being audited is 9%. Find the conditional probability of being audited in a specific year given that you already got a speeding ticket. So then that's just exactly the probability of both events happening, audit and speeding, divided by just the bottom, the probability of speeding. So this always just goes on the bottom by itself. So whatever the second one is goes into the denominator by itself. So it's both audit and speeding. Well, they said the overlap of that is 9%. And they said the chance of getting a speeding ticket is 12%. So, you got a 75% chance, if these were correct, if you already got a speeding ticket, and both audit and speeding happens 9% of the time, and you already got a speeding ticket, then there's a 75% chance you will get audited given that you have a speeding ticket already. Ooh. All right, let's see. Suppose that the probability of me going to Hawaii is 70%. That's not real. And the probability that I go golfing, given that I am in Hawaii, is 50%. Also not real. Find the probability that I play golf and go to Hawaii. All right, so again, this is the almost the same setup here. The probability of golf and Hawaii is going to be the probability of Hawaii times the probability of golf given Hawaii. So these are two different problems. I'm sorry, I said they were similar. They're not. This is, what are the chances you get audited given you were caught speeding? This is different. This is an and problem that is dependent because, golfing in Hawaii. So we do the probability of Hawaii times the probability of golf given Hawaii. And so you're just going to multiply those two. So it's 70% chance that you're going to Hawaii and a 50% chance you're going to golf given you're in Hawaii. There's only a 35% chance that you're going to go golfing and go to Hawaii. Okay. All right. The next video will be on 4.4, the counting principle.